All right. Well, so let's start. Today is about the wide field slit-less spectroscopy demo from Chris Willett again. Thanks, Chris. And well, you can go.
Okay, thanks, Luke. Yeah, so last week we were talking about the multi-object spectroscopy with NIRSpec on JWST. And this week we're talking about slit-less spectroscopy, and maybe compare a little bit the multi-slit with the slit-less modes. So we'll start off talking about the different slit-less modes on the two instruments that do this on the telescope, and then later on we'll demo some of the tools as usual. So wide field slit-less spectroscopy, the two instruments that do this on the telescope are NIRISS, the Canadian instrument, and NIRCam. As you remember from the introductions about the instruments, NIRISS has a single detector that's 2.2 by 2.2 arc minutes across. And then NIRCam has twice the field of view in two separate modules. And NIRCam also has the long wavelength and the short wavelength arms. So for NIRCam, slit-less spectroscopy is only done in the long wavelength arms. So that's from 2.4 to 5 microns. And NIRISS only does slit-less spectroscopy in the low wavelength end of NIRISS's range. So basically from 0.9 to 2.2 microns. So basically, depending on the wavelength you're interested in, determines which instrument you should choose for slit-less spectroscopy here. They were basically designed on purpose to not, duplicate each other by doing the same wavelength interval. So the major difference between the two instruments in terms of what they're doing with slit-less spectroscopy is the spectral resolution. And NIRISS's spectral resolution is approximately 150, whereas NIRCam's is 10 times higher at 1500. And so we'll talk about some of the consequences of that later on. And of course, in NIRCam, because you do have these two fields of view, you can be doing slit-less spectroscopy in each of the two fields at the same time. So what are we doing with slit-less spectroscopy? Basically, we put a grism in the optical path, and we take a spectrum of every source in the field. And then, so obviously, because fields tend to be crowded, especially with the extreme depth of James Webb, there'll be overlap of different spectra. So you can see on the right-hand side here a simulation of a low redshift massive lensing cluster field, which has been observed by HST in the Frontier Fields program. You can see that on the direct image is the top image of the three here in orange on the right-hand side. And there you can see these very large elliptical galaxies that make up a large part of the mass in the stellar mass in the lensing cluster. And then there's also a lot of lensed background sources. And you can see that if we now use NIRISS and slit-less spectroscopy mode, looking at the lower two images, we now put the grism in the path, and this basically disperses the light along one of two directions so that we get a spectrum for every single object in the field. And in the center, where the field is very crowded, we do get overlap between some of these objects. And so we'll have to be able to disentangle how much the light comes from one object or the other. So one of the great things about the slit-less spectroscopy is you have this extremely high multiplex factor. You're basically getting a spectrum of everything in the field. If you followed last week's webinar about NIRSpec multi-object spectroscopy using the micro-shutter array, you'll have seen the limitations of that in that you can only open shutters on certain targets in the field. So you have to select the targets of highest priority that you want. Here you get all the objects in one go, but of course you have a more limited wavelength range to stop these spectra being too long and having even more overlap. And you also have a higher background because the background across the whole field is also being dispersed across the whole detector. Whereas with a micro-shutter array, you manage to get low background by only opening certain shutters onto the detector. So with both NIRISS and NIRCam, we have the two orthogonal grisms. So that's what you see here in the lower two pictures on the right, is that the spectra are dispersed along the horizontal direction in the middle and in the vertical direction along in the lower panel. And what this means is that if you may have contamination where a source is obscured by a spectrum of a brighter object, in one of these two directions, it may be clean in the other direction. So it allows you to get a higher completeness of getting a good spectrum for each source by being able to disperse in these two different ways without having to rotate the telescope. So with HST, HST has grisms, but they don't have orthogonal grisms. So if you want to get some rotation of the field, you basically have to roll the telescope to do that. And with James Webb, it's there's a lot of constraints on how much you can roll the telescope. So instead, both instruments have this system where you can disperse using orthogonal grisms. Another advantage of slit-less spectroscopy is you don't need any target acquisition. So we talked last week about target acquisition with the MSA, and that you have to have all these reference stars with very high level astrometry. We don't need that at all here. You just point and shoot. But the thing you do need here is you do need to take the direct image, like the top panel on the right, so that you have a good idea of the shape and intensity of light from the different objects in the field, because you're going to need that to be able to model how you match up the spectrum of each object. So to know exactly where each object is and what the wavelength is, you do need to spend some time, and typically it's around 5 to 10% of the exposure time in direct imaging without the grism in the path. In NIRISS, the way that the APT templates are set up, this is mandatory that you have the direct imaging. For NIRCam, it's actually optional, because you do have the option of using the shortwave detector to get an image instead. And then at the bottom here, there's a simulation of a galaxy in the Hubble Ultra Deep Field at redshift 2.1. And so there's a combined color image on the left-hand side, and then the spectrum using NIRISS of this galaxy in the grayscale panels, using 3 different filters with NIRISS, which cover a spectral range between them from 1 to 2.3 microns. And you can see the bright emission lines here. And one of the features of slit-less spectroscopy is that you can model the continuum spectrum and subtract that off, and that's been done. And in the lower panels there, you see what the residual left behind once the continuum has been modeled and subtracted off. And what you now have is, in each of these panels is a map of the emission lines. So you can see on the left-hand side there's the O2 emission line, in the center is O3 and H beta, and then on the right-hand side is H alpha emission line. So you can get maps of emission lines with this technique for a very large number of galaxies at once. Okay, so that was NIRISS. Moving on to NIRCam, where we have the higher spectral resolution. And this higher spectral resolution obviously means as well that you have longer spectra. So if you look at the top there, that's basically showing you for using different filters from F277W down to F444W. It shows how much of the detector space gets taken up by each individual spectrum. You can see in the wide filters, it's typically half to even more than half of the detector size gets taken up by each spectrum, which is quite different to a NIRISS, which had the much shorter spectra. And the other factor here as well is that some of the spectra will be falling off the ends of the detector, depending upon the certain field placement. And that's kind of illustrated in the images in the lower, which are some simulations from Noor Pirskal at Space Telescope Institute. And there's the direct images on the left, and then we have simulated spectra of those fields using 3 different filters. And you can see that some of the spectra that fall on the detector in 277W are falling right off the detector in 444W. So you're only actually getting part of the field with the spectrum over the whole range. So sources near the edge of the field will lose some of their wavelength range. And so that's something to check out if you're interested in a particular wavelength range and in a particular part of the field. Then you might want to make sure that you're actually going to get the spectra for those covered, and you're not going to be losing those parts of the spectrum. One thing to note, as I mentioned before about NIRISS, in that simulation, that you can basically get a map of the emission lines. With NIRCam, you have to be a bit careful, because the higher resolution means that you may actually be spectrally resolving the emission lines in larger galaxies. So you may not actually get a map of the emission line. It can be kind of smoothed out due to the velocity structure in the galaxy. And as I mentioned before, with NIRCam, you can also use the short wavelength arm of each module to obtain short wavelength imaging at the same time. Okay, so one of the things we have to think about whenever we're doing any kind of imaging or spectroscopy observations is dithering. So we have special dither patterns that are set up for the different instruments. NIRCam basically follows the same kind of dithers that are used for NIRCam imaging, and these are to fill in things like the gaps between the two modules and the gaps between the detectors at the short wavelength end. Obviously, the gaps between the shortwave detectors aren't an issue for the GRISM, which only uses the long wavelength. And then we have small dithers as well, which are on the sub-pixel scale to improve the pixel sampling. With NIRISS, we have multiple dither patterns from between 2 to 16 points, and they come in 3 different sizes depending upon the size of the target area you're looking for. So how much, if you have large galaxies that you want to put that large object in, I mean, not large galaxies, but even, a few arc seconds across intermediate redshift galaxies, and you want to move them onto different pixels the whole time, then you might want to go for the large dither pattern. Smaller dither pattern might be good for point sources, or the medium for a typical kind of distant small galaxy field. Now talking about the infrared detector readout. You've probably seen this before if you've attended some of the other webinars. The detectors are read out non-destructively so that we can basically improve the signal to noise at the end of the ramp instead of just reading at the beginning and the end. We read out multiple places along the ramp, and move on. So NIRCam has a whole range of readout modes depending upon how bright the source is. So in general, for long exposures, you're using the medium or the deep readout modes, whereas for bright objects, you might be using the rapid or bright or shallow readout modes. And then NIRISS is much simpler, just has 2 readout modes. There's the rapid mode where we're reading out every single frame every 10 seconds, and then the NIRISS where we average 4 frames and we're reading out every 42 seconds instead. And again, the choice of those will largely just come down to the integration time. You want to make sure you get a decent number of groups read out as you're going up the ramp. So if you have long exposures, then use NIRISS. If you have short exposures, use NIRISS rapid. Okay, so the observing sequence for slit-less spectroscopy, we need to choose what filter we want. So the filter decides what wavelength range your spectra are going to cover. We need to look at the pre-imaging, decide how much exposure time is required for pre-imaging, and then select one or both of the GRISMs, choose a dither pattern, choose the imaging to do after the observation. So the kind of, although it's called pre-imaging, it's really direct imaging, and you get one exposure at the start of your dither sequence, and then you get another exposure at the end of the dither sequence. And then we have for NIRCam, you can do extra imaging, because as I mentioned before, the NIRCam spectra are so long that you get a significant amount of as well as losing spectra out of the edge of the detector, you also get objects from out of the field which have spectra that fall on the detector. So if you want to know what objects those correspond to, you need to do some extra imaging to be able to get those. And then obviously we can change filter and repeat these sequences, or change GRISM and repeat. Okay, so parallel observing. In cycle 1, certain combinations of parallel instrument modes have been allowed. And for slit-less spectroscopy, the NIRISS slit-less spectroscopy is allowed with NIRCam imaging and also with MIRI imaging. In cycle 1, NIRCam slit-less spectroscopy is not allowed in any of the parallels. Hopefully by cycle 2, that will be allowed to observe other instruments while you're doing NIRCam slit-less spectroscopy. But that's not an allowed mode in cycle 1. And then, yeah, mosaicing, that's if you're covering a larger area. So covering regions, a significant fraction of the detector size. Okay, so we're going to talk a little bit about a science case, and then I'll give a brief introduction to that. And then after that, Loic will talk about using the exposure time calculator for the science case. So here's the reminder, the proposal deadline is coming up soon, April the 6th. And if you want to write a proposal, then the steps to go through, look at the visibility of your target, look at the exposure time calculator to see how long you need, and then put everything into the APT. So today, Loic will look at the exposure time calculator, and then I'll run through using the astronomer's proposal tool. So this is the program we're highlighting today. This is a Canadian guaranteed time program using NIRISS slit-less spectroscopy to look at some massive lensing clusters. So the idea is we're looking at galaxies within the reionization epoch and also at more intermediate redshifts to study the evolution of low mass galaxies across all of cosmic time. The method here is to use NIRISS slit-less spectroscopy and also NIRCam parallel imaging, and also NIRCam imaging of the actual field where the cluster is to get a longer wavelength range, instead of just what we can do with NIRISS slit-less spectroscopy, which covers the 1 to 2 micron range, but also image with NIRCam out to 5 microns. And the field here will be a crowded field, as I showed at the beginning, especially in the core. Here's just 1% of the simulated field here with a direct image on the left and the dispersed image on the right. And you can see that when you look at the dispersed image, and this is well away from the core of the cluster, a significant part of the detector is covered with spectra from sources. And there's some overlap of the spectra as well. So we really need to be able to model the spectrum based on the direct image. There's a galaxy, that it's going to have a spectrum, exactly where that spectrum is going to be, so then you can model that to recover the spectrum of each galaxy. Okay, I think over to you then, Loic.
Okay, thanks, Chris. Is there any questions so far? I'll take that as a no. Okay. So yeah, see, the modeling is interesting. So with the crowding here, what we're going to do with the ETC is to have 4 sources in the field to see that they contaminate, if you want, the extraction of the spectrum. So I'll create a new workbook here and load it. So this is a webinar 7. And so we'll go first, as usual, in the source pane. And we'll create 4 sources. The first source is going to be your science target, if you want. It's going to be an emission line galaxy, but seen from a distance and considered as a point source. So the emission line is our target galaxy. So I'll create you I'll use no continuum, so we only see the emission lines. We will not renormalize, we'll put emission line intensities here. So in lines, I'll create 3 lines. So let's start with line 1. It's going to be centered at 1.15 microns. We'll use a 1,000 kilometer per second wide line. And we use this flux of about 10⁻18 erg per second centimeter squared per second. And we'll add this line. Okay, so the wavelength was chosen because it's right at the center of the first of 3 filters that we're going to use. Okay, we'll do a second line with the same width and intensity, and a third line at 2 microns. Okay, so we got 3 emission lines. We'll save this, and this should be seen here at the bottom where you see the spectrum of the source. Next, we'll consider it's a point source because it's the core of a very distant object. And we'll make sure that we have it in our scene so that we can add an offset in the scene where we're going to position it. It's going to be at -1 arcseconds in Y and say 0.5 arcseconds in Y. So let's save this, this first source. And we'll do 3 more sources that will be a bit different. So let's create a second source. This time it's going to be a flat continuum galaxy with AB 26 magnitude. We're gonna so it's gonna be a flat, as I said. We're gonna renormalize it to a magnitude, a NIRISS filter magnitude, a NIRISS imaging of, say, this filter. So we have this intensity here. There's no line in this galaxy. It's just a flat continuum. We're also considering it a very distant object, and so there's no shape. It's a point source. And we'll add the source. Oops, we'll add the source to the scene so that we can apply an offset to it. So here we have a second source. We could show both spectra together here. They would show here two different spectra. Next, we'll add the third component. This time is a starburst galaxy. Okay, so starburst. We'll use a library spectrum of a galaxy of NGC 3690, and we'll place the galaxy at a redshift of 2 and renormalize it in the AB mag of 25 in the NIRISS imaging filter save. So you see the spectrum here of a nice starburst galaxy, lots of emission in the infrared. We won't add line here. The shape is going to be an extended Cirsic profile with semi-major axis of 0.3 and the other axis 0.15 arcseconds with this Cirsic index for the shape. Okay, we can save it, and we'll add this source to the scene. So we now have 3 sources. We could actually position it now. We'll leave it at the center and just give it a small rotation just for fun. Okay. So as you can see, I mean, you can build very complex scenes if you want. So there's one more source I want to put, but first I remember maybe I made a small mistakes in the second one. Did I do it properly? No. See, I forgot to do this. This should be 26th magnitude, I believe. Yeah. Okay. So let's go back to a final source. This time it's going to be a flat continuum point source again, but very faint. Okay, so it's a faint AB 28 galaxy. It's going to be a flat continuum again, and we'll normalize it to 28 AB. Okay, no line, no shape, it's a point source. Let's save this, let's add it to our scene. And now we'll put it in a different position, put it at 1 and minus 1.5. So here we go. We have four sources in our scene. The target of interest is the top left one. It's the one with emission lines at high redshift galaxy. at a Z of 25, maybe not, a large Z. Okay, and we can proceed with doing calculations now. Okay, so we'll be using, we'll do two calculations today for this demo. We're going to do the wide field slit-less spectroscopy of NIRISS in one filter, the F150. And if time is left, we'll do the imaging in one filter for NIRISS as well. Because during the WFSS sequence, you have imaging, then GRISM spectroscopy, then imaging again, as Chris said. So we'll start with the WFSS with NIRISS. So those are faint galaxies, so we'll aim for having a signal-to-noise ratio between about 3 and 4, something, you know, at the limit of what you consider a detection. And depending on the exact parameters that you put, especially for the aperture extraction, you may get slightly different results. So I'll show you that. I'll show you what I mean a bit later. We know those things are faint. So the first limiting factor is going to be the single exposure time. So let's start by making sure that we're looking at this emission line galaxy. We are okay. We'll put the proper background for this galaxy. So this lensing cluster galaxy MAX 0416 is at this RA deck. And it's important because the background may vary a little bit for different positions in the sky. The background to do zodiacal light. And so we have our background, we'll consider it a low background. Okay, we'll use this GR150 and the filter is going to be 150. So red message saying that our extraction and strategy is not within the chosen filter, so we'll change the wavelength of interest to 1.5. We'll center the aperture on the emission line galaxy. And then something I'll do here is I want to mention what is the aperture half height. Okay, when you're doing a spectroscopy, the extraction aperture is not circular like for imaging. It's actually it's a rectangle, so it's a 1 pixel wide by this number high. Okay, actually this is the half height. So the nearest pixels are about 65 milliarc seconds in size. If you had if you put 4 pixels together, it's about this times 4, so 0.26 arc seconds. So here's the half height, so I'll choose half of 0.26, so 0.13. So just to get a round number for the extraction, because I want to show you the sky level. Okay, but it's pretty close to the optimal aperture extraction. Also, the background, how do you subtract the background? Here, Chris showed that there's going to be tons of contamination, okay? And indeed, if you select, if you don't carefully select where you use your background pixels, then you may get bad results. Here, the most optimistic case is if you consider no contamination by those sources, and that's what we'll start with. We'll start with no contamination by the other sources, and I'll show you later what happens when you do consider those other contaminants. Okay, I think I'm almost ready to launch a calculation. First, okay, those are faint galaxies, so we are going to do the maximum exposure time. So about 20 minutes is about the maximum you can do on a single ramp. Here, 20 groups is 14, so 28 is about 20 minutes. You don't really want to go any longer than 15 to 20 minutes for a single ramp, because as I said before, the cosmic ray starts to contaminate a lot of your pixels. and you lose many of them. I mean, you don't lose the pixels. It's more difficult to fit a ramp slope to the ramp. So we'll use this and do our first calculation. As Chris mentioned, the wide field slit-less has a higher background than NIRSPEC MSA slits. And I'll show you what is the background that we get. So here, a single exposure gives you a signal to noise ratio of only 1.2, not enough. So we'll need more integrations. But I'll show you, nevertheless, what happens on a single exposure by looking at the report. Okay, in the report, you have the signal to noise ratio here, but you also have it towards the end, the total background flux in the extraction aperture. Here we are, this flux 3 electrons per second is within 4 pixels. So basically each pixel is about 1 electron per second, and we have an exposure of 1200 seconds. So typically in the background of those images, you have about 1200 electrons of background photon noise. So that gives you an idea. It's a very small fraction of the full well of the detector, but still, it's more than you would get with NIRSPEC, for example. You could download the image to see what it actually looks like. So we'll look at the image here, the detector image, so-called. You see that you basically get the start of a trace from the big galaxy at the center, but you have no detection. And the background level, if you look at the values, it's about 0.8, 0.7, 0.8, so roughly the 1 electron I was referring to per second. Okay, so it's all consistent. So let's now try to see what's the actual number of integrations that we need to reach a signal to noise of 3 or 4. I'll first remind you that the WFSS with NIRISS uses 2 orthogonal grisms. So that means that the number of exposure is going to be a multiple of 2. And so I'll use the expand integration tool here to basically explore what are the integrations that we want. So we'll start with 4 integrations and step by 4, and we'll do 5 iterations. So that creates 5 calculations. So hopefully one of those will reach 3 or 4, and they do. So we can plot those results here. You see that the emission line galaxy peaks at 1.5, and the background is well subtracted because we chose the noiseless subtraction. So we see here that basically this setup or that setup give you 4 of signal to noise ratio. I'll pick the number 5 calculation here to be in agreement with the APT later. Yeah, so let's look at what the detector image looks like. It looks like this. Our galaxy, our emission line galaxy is here. So I'm gonna make sure that indeed we're looking at the emission line galaxy SNR. That's the case. So let's download the image for the the one that seems good. Okay, so it's still very weak, but it's this beast here. This is the emission line galaxy. It's not a, you see it's only, it looks like a point source. Good. Okay, so that one, we can delete the other ones if we want, but this one gives you 16 integration to get what you want. We'll split it in actually exposures because we're doing dithering and moving between the two prisms. So it's actually 16 exposures. Okay, so at this point, I wanted to show you what the strategy we choose, how does it impact the background subtraction strategy, how does it impact the signal to noise that we calculate. So I'll select the background subtraction by choosing a region here. If we chose a region that's very close by, so just close to our the other contaminants, it's gonna worsen the results. So let's calculate. We're starting with 4.66, and let's see what happens when we use a different background extraction. We're going to subtract some, the background is going to be contaminated by the adjacent sources. Okay, so you see here that the signal to noise has decreased. I'll hide the other calculation here, but basically take a look at the signal to noise as a function of wavelength. You see that there are weird negative values, and that's because of the flux in the nearby traces. Okay, so if you instead had picked a distant position, something like 2 arc seconds, between 2 and 2.5 arc seconds, then that's it's devoid of contaminants, and that would produce something close to the noiseless background that we had before. Okay, so after this calculation completes, I can go briefly on the imaging. It's something we've seen before in previous webinars, but just as a reminder, I'll try to go quickly. So you see that this SNR has changed. So it has moved between 4.6 for the noiseless sky background to less than 3 for the bad background selection, to 4 with this medium or in between selection. So you see that the signal to noise ratio can vary a little bit depending on taste on some parameter choices. Okay, so imaging with NIRISS. I'll create a calculation here. Imaging is allowed here just for the sake of using direct imaging with WFSS. You cannot use NIRISS imaging by itself. It's not allowed yet. Okay. So we'll use the same scene. I won't bother with the background, so I'll just pick the instrument setup, and this time, I mean, imaging goes faster than spectroscopy. We will use 4 exposures because of the sequence of WFSS. It goes with imaging, GRISM 1, imaging, GRISM 2, no, sorry, imaging, GRISM 1, imaging, then imaging, GRISM 2, imaging. So 4 exposures per when you use the 2 GRISMs. And so we'll try this with centered on the emission line. Now you have to play a little bit to reach the signal to noise that you want. It's again about 3 that we want. Okay, so we don't quite reach it, but at about 20 or so, we get the 3 or 4. And you see it here. You see this faint source there is your target, and you get the signal to noise of 3. So those are. This is what I wanted to show with the ETC. So Chris, or maybe there's a question for this part. If not, Chris, take it away. Maybe you're muted.
Okay, you need to unshare your screen first. Can't steal it for some reason.
Stop share, yeah, okay.
Okay. Okay, so you should be seeing my APT screen now.
Yeah.
Can you see it?
Yeah.
Okay.
Yes.
So we're going to start a new document. That button's not working for the moment. So we'll go up here, new JWST proposal. And then we have all the usual stuff you have to fill in: the title, the abstract, category, you know, again, scientific category. And then here's where you attach the PDF with your science justification. I'm going to skip that and move straight on to the targets. So because the target we're using for this proposal is a well-known galaxy cluster, we should be able to find its position automatically from in a database. So here's its name, search, and there it is. So we'll use that as our target. Okay, and then we need to say what that's. So it's a cluster of galaxies. It's a rich cluster of galaxies. And we don't need to fill in anything else on this. So we'll move straight on to the observations. We need to make a new observation folder. Okay, so this is going to be NIRISS prime instrument, wide field slit-less, on max J416. So we choose the instrument as NIRISS, and then we choose the WFSS template. And then in this case, we want to get parallel imaging with NIRCam nearby. So we choose a coordinated parallel. And as I said before, the 2 options, you can use MIRI in parallel or you can use NIRCam. So we're going to want to use NIRCam this time. Select our target. There's our target that we already specified. So this is basically set up the target and the start of the template. Then we move down, and here's where we really set up the science observation. Because of the way the observations are structured with templates, there's very little for you to do to actually set up an observation like this. So the most important thing here is the dither and the dither pattern size. So the dither is going to tell you how many exposures you have. And there are multiple different dither patterns in here. So we have the numbers from 2 to 16, which are the regular NIRISS dither patterns. We also have these other ones, which have slightly different offsets that have also been optimized for subpixel sampling with NIRCam, if you're doing NIRCam in parallel. But in the current example, we're just going to use one of the NIRISS dither patterns here. So we'll use the 8-point dither pattern. So I'll get 8 GRISM exposures in each sequence. We have the choice of these sizes I mentioned before: small, medium, and large. We go with medium here. And then we can basically add as many sequences as we want. So we'll add one here. And then you have the choice of GRISM. So you can either, in each sequence, you can either choose one GRISM or you can choose to use both. In the example here, we're going to do both GRISMs, but we're going to choose them individually. And the reason for that is it gives us more flexibility in selecting a wider range of NIRCam filters to do in parallel. So we're going to choose GWSM there, and then one of the filters, this one. And Loic just mentioned in the ETC the signal to noise that we need to get. Basically told us how many groups we need. So he had 8 separate integrations or exposures, and each one had 28 groups. So we're going to put 28 in there, and we're going to leave just one integration per exposure. You can, if you want, you can put multiple integrations in for each exposure. So you could, for example, so the total exposure time here now, 8-point dither pattern, you can see is 9,700 seconds. What we could do instead, we could say, well, I'm going to split each exposure, integration, get 2 integrations per exposure, and then each dither position you get 2 of half the length, and then you see the exposure time is still approximately the same here. But we'll just stick with doing it like this. So this has specified the GWSM part of the observation. Now we also want to specify the direct image. So the direct image, which Loic was just showing the ETC for just now, we're going to go with 13 groups. It should be enough. And again, 1 integration per exposure. And so then you can see at the bottom here, so these 2 parts here are the parts you fill out, the science observation and the direct image exposure parameters. And then the part at the bottom isn't editable, it's just a display of the actual sequence that's going to happen. So we start off with 1 direct image in the 115W filter. Then we do this 8-point dither pattern with the 115W filter and the 150C GWSM. And then at the end of that, in the final dither position, we take another image. So you'll get 2 direct images here taken in different positions. And so each one of those is 570 seconds. So for this program, we actually want to, well, actually, I'll move on now and talk about the NIRCam imaging. So while we have this kind of simple sequence where we have 1 direct image, 8 exposures with the GWSM, and then 1 direct image after. Actually, I'll just duplicate this first, because we're also going to want to use the same filter, but with the R GWSM. So the GWSM that's orthogonal and disperses the other direction. So now we basically have exactly the same thing again, a second sequence, where in the second sequence we are using the other GWSM. So you see we get direct image, then 8 GWSM images, 2 direct images, then 8 more GWSM images, and then finishing off with 1 direct image. Okay, any questions so far? Okay, so then I'll move on. So in parallel, we have this NIRCam imaging. So with NIRCam, we're going to use both of the modules to get as much area as possible and a full subarray. And then basically what we need to do here is we need to add 1 line here to match each line that we have here. So here we have basically 6 different lines in the exposure display. Some of those have a single integration, some of them have multiple integrations. But in the NIRCam setup, we need to get 1 line that matches in terms of not exceeding the exposure time in each of these. So with NIRCam, we have the 2 different wavelength regions, the short wave and the long wave. So the short wave, we'll go with this filter, F162W. Long wave, go with F300M. And the readout pattern here. So this is one of the short observations that's associated with the direct image. Shorter ones, we'll use the medium 8 readout pattern because that's appropriate for around about 600 seconds. And then if we set that up with 5 groups and 1 integration, the total exposure time here is 526, which matches up with the first line here, which was 569. So it's got to be less than this value, although it also takes into account the overheads, which aren't included in this value. So a bit of trial and error will show you that if you tried to get an extra group here and increase this 526 up to 630, then now your integration time with the parallel instrument is too high. So you can't do that. So you get this red X warning that the parallel duration, so the exposure plus overheads, is at 691, seconds, whereas the prime is only at 590 seconds. So we can't do that, so we have to go with 5. Okay, and then, so for the second line, so now we're basically matching up with the GRISM, the 8 integrations with the GRISM, which are longer exposures. So we'll use the same filter again, but this time we'll go for the deep 8 readout pattern, which is for longer exposures. And in this case, we got total exposure time 7,600 seconds, which is a bit less than the 9,700 here. So you can increase that a bit more to 6 groups. It gets close. If you try and go up to 7 groups, then we get the red X because we've exceeded the prime exposure time again. So we have to keep that down at 6, like that. Okay, and then we would want to match up one parallel line for each of the prime lines here. We have 6 lines here. So we need to basically duplicate this one again and then move it. So now we have the short one, the long one, the short one, which matches up. And then we could basically duplicate all these again, maybe choose a different filter this time. Okay, so now let's do a different filter. Let's go FO90W in all these. And F250W, 250M here. And there. So now you see that we've matched up. We've got 6 lines here, which matches the 6 lines here. And if we look at the total amount of time we're spending doing NIRISS observations, it's 2,100 seconds. And in NIRCam parallel, we're getting 15,000 seconds. Okay. So obviously, if we decide that we actually want to get, or say, more filters as well, because there are these different filters you can use with NIRISS spectroscopy. In this project, for example, we actually using the 115W plus the 150 plus the 200. So we can add those as extra lines here, and then we get a much longer list here. And then in NIRCam, we can add more NIRCam filters for our parallel fields. We can end up getting a large number of parallel filters, but I'm not going to go through all that now because it's a bit repetitive. But that's basically the observation complete. So this is a single field observation, so we don't have any mosaicing. But if you wanted to do a mosaic of multiple pointings, then they can be specified here, and you can define how much you want the separate pointings to overlap. There's the special requirements tab here. If there are special requirements that need to be added for the dates or the position angles, or if you need to make some offset between different observations, you can do those kind of things here. Another thing to note here is this background limited tab, and there's extensive information on JDocs about this, and a background tool you can get. This basically lets you set, because the background changes during the course of the observing season, you can basically set the background noise to not be higher than a certain level above its minimum, so 10%, 20%, 40%, 80%. And if you do that, then it does affect the schedulability of the observations. So you want to be careful doing that because it may be too hard to schedule if you say you absolutely need the lowest background. But as Loic showed in the ETC, these observations are background limited, not detector noise limited. So you may well want to consider what the background level is. Actually, I'm going to take that out for now. So I'll just show in Aladdin. What we have here, just load an image. So now we have the NIRISS observation centered on the cluster is here, this blue square here, and then the NIRCam parallel field will be over here. And if we change the contrast a bit, we can see, you can just about even see in 2 mass, well, it's kind of hard to see, but there are these bright objects, or very faint in 2 mass objects here, are the cluster galaxies showing the field. And then let's check with the visit planner. I want to make sure that this is actually an observation that you can do, and check when you can do it. So let's go to the observation and the visit planner. We're going to update And so now we're checking when, during the course of the year, you can actually carry out these observations. And these lines here show you the dates over which you can observe. So there's quite a large visibility window in which you can observe this field. However, if you were to add this background limited and say it must be no more than 10% above the minimum. Now if we go back to the visit planner and run that again, we'll update it. So these were the large visibility windows we had before. And then when it updates, you see that it's cut down some of the time which we observe when the background is higher. And depending upon where your field is, how close to the ecliptic, the effect of adding that constraint can be more drastic than other times. So here it's not too bad. We still have quite a large amount of time where we can observe the field, but some fields with the highly variable background, you get much worse, much more constrained observing dates. Okay, so are there any questions?
Yeah, Chris. So with parallel imaging, is there a price to pay in the overheads? And I mean, do you have to pay a small amount of time to for?
Yeah, it's a good question. So if we look here, where we have the total amount of time that's charged, it's 30,753 seconds. Okay, so if we turn off the coordinated parallels. Now, if you're going to do this yourself, I warn you that if you turn it off and turn it back on again, you've lost everything you've entered for the parallels, so you want to be careful about doing that. But we'll just turn it off now. And that's so interesting. The science time went down as well.
Oh, well, I shouldn't have asked that question.
I don't know what happened there. Oh, okay. Well, it's totally changed what it's doing now. So that seems to be an APT bug, where if you put in the parallels and then take them out, it does something very strange. Because it's not doing what it's supposed to now. So we're supposed to have
8 dithers, right?
Integration. Yeah, it's supposed to have 8 point. Okay, so it changed the dither pattern on us. There we go. There we go. So we go back to 8-point dither pattern.
Yeah.
Now we have the same as science time as before, and the total charge is 29,460 seconds. So it was costing us about 1,200 seconds in extra overheads. And the main component of that is in the mechanism times to move the filters in NIRCam.
Okay.
So in total, it's a pretty small fraction of the time. If you have long exposures or long sequences like this, then it's fairly cheap to make parallel observations. But you do have to, have a good science justification as well in your proposal.
Yeah, and you don't have to be picky in terms of where the NIRCam imaging happens, right? It could be, depending on the schedule, it could be anywhere around. Again,
it depends upon your science. So if you really have a strongly, if you really want to constrain the orientation of one field with respect to another, you can do that if you have a good science justification.
Yeah.
And if it's actually possible if it fits within the visibility window. But if you don't care exactly where the field is, you just say, well, I know it's going to be close to a galaxy cluster, so it's going to sample galaxies just outside the cluster. But you don't care in which orientation, then yeah, you don't need to specify it.
Any other question? I do have another question. I know that for calculating the time required for your fields for Canucks, you may have used the ETC, but I think you had your own tools to do simulations. And do you find that it mostly agrees with what the ETC outputs?
Yes, so in terms of the signal to noise, yeah, we agree. I mean, as you know, the instrument team also put in, compared the ETC values while the ETC was being developed with our own instrument team values for the sensitivity. So we agree from that point of view. And then really the difference here with the slit-less spectroscopy is that it crucially depends upon how much contamination you have and how you can deal with that contamination. When you do get, you know, other bright sources nearby or partially overlapping, and then it really becomes a kind of nonlinear problem that you can't get right in the ETC. So the ETC does a very good job at telling you exactly, you know, for a certain situation, you know, what the theoretical sensitivity is, but it doesn't tell you how well you may be able to subtract contaminating flux from a nearby object. And that's something that you really only get to by using a GWSM analysis software, which, you know, some of which are available now. So
yeah, good.
Okay, thanks.
Well, thank you very much, Chris, for this nice presentation for last week as well. You're an expert on this topic, so it was really great to have you. So if there's no other question, I'll let you go, and we'll tell you that next week is our last webinar. This time it's going to be on coronagraphy. So it's